Now, as a third topic of today, let's discuss the relationship between shear force V and moment M. One thing I want to ask you is let's try to look at previous example force and moment diagram. So what you can see here is you have somehow decreasing magnitude of V in linear term, and you somehow see that the slope of M in originally was positive and large, and this positive slope is decreasing. At some point the slope becomes zero when V becomes zero, and you see that negative slope starts. As you can see, negative V starts, and at the right end you see like a large magnitude negative slope, and the right end you have large negative number for V. And regarding for the previous problem, you have constant slope, you have constant positive v, you have constant negative slope, you have constant negative value of v. So what you can see from previous example is that maybe if we obtain just one, like either shear force diagram or moment diagram, we can obtain the other automatically based on this relationship, right? So let's see if our observation is true, and let's also see that if we can derive this based on mechanical equilibrium. So for that purpose, because we set the sign convention for shear force and moment, we're gonna set the sign convention for external force and moment. For the external force, from the force downward, from the external force, downward force Q, downward point force P, downward force will be defined as positive sign in our textbook. Okay, so the relationship we're gonna get regarding V and M and external loading, we'll consider downward external loading as a external force as a positive sign. Regarding the external moment M, we're gonna set counterclockwise moment as a positive sign. Okay, so let's start from the distributed loading first, and then we're gonna move on to point of force, and then we're gonna move on to shear moment. So regarding the distributed loading, let's try to take some small volume with delta x. Okay, and for this infinitesimal volume colored here, we can draw free body diagram like this. We have external force, which is specified as color in red color, and we have force left and force right, and we have moment on the left and moment on the right. So we set positive sign convention direction for both left facing and right facing surfaces. And for small delta x, very small width, we can set this distributed loading as a constant number. So let's set positive upward force as positive sign and try to sum up the force in y direction. So we have Vx, we have negative Vx plus delta x because it's downward, and we have this downward force Qx multiplied by delta x to recover the dimension of a force, because Qx means force per unit length, and its direction is downward, so you have a negative sign here, and these must be summed up to be zero to satisfy mechanical equilibrium. What you can realize is difference between Vx plus delta x and Vx can be written as minus Q delta x. Now, if you move delta x to the left hand side and try to take the limiting case of delta x goes to 0, you see that this left hand side becomes to be dv dx, and right hand side becomes to be negative qx. So this is the relationship between distributed loading and slope of shear force diagram. Okay, so, and this holds for any arbitrary distributed loading qx. Now let's set counterclockwise moment as positive sign and try to obtain the moment with respect to center point C of this infinitesimal volume. So and of course the summation of moment must be 0. So you have clockwise moment on the left facing surface. So you have minus mx. You have counterclockwise moment on right facing surface, so you set that as mx plus delta x. Now you have clockwise torque, and the distance to the force is delta x over 2. So delta x over 2 multiplied by vx, which is clockwise torque, which must be negative sign. You have negative vx delta x over 2, and you have another clockwise torque, vx plus delta x multiplied by the distance delta x over 2. So you have this additional term. So if you sum up these four terms, they must be summed up to be 0. And if you take out this delta x to the left hand side and take this moment as a left hand side, this is what you're gonna get. And what you can realize is that when delta x goes to 0, they becomes almost the same as each other. So you can say right hand side as simply vx, and left hand side becomes to be a slope. So what you can see here is dm dx, the slope of moment diagram, must be same as shear force v at the specific location. So we can set rule 1, and rule 1 is about distributed loading qx. When you have a qx, qx can be 0, and the v prime, the slope of v shear force diagram, must be same as minus q, and slope of moment diagram must be same as force diagram v. Okay, and it was consistent with our intuition. So when we have linear distribution for this distributed loading, what we have found is that because it has constant qx over the entire sample, we have constant slope for the shear force diagram. Because we have constant slope for the shear force diagram, and this slope changes from positive, the sign of v changes from positive to 0 and negative. We have moment diagram starting from slope positive, 0 and negative. And we have a similar relationship in problem B. So we have constant v and constant v with respect to this 2 kilonewton point of force. Because we have positive force here and negative force v here, what we have found about moment m is we have linearly increasing moment and linearly decreasing moment before and after the 2 kilonewton point external force. Okay, so this is the rule 1 we found about distributed loading qx. And as a second rule, let's consider point of force. So for point of force, we can take out imputational volume around point of force and try to consider force and moment diagram. Regarding the force diagram, we take upward as positive sign for this specific summation. Regarding this, you don't need to worry about the sign convention. Because this is independent from the sign convention we chosen before. You can choose either this as a positive sign or this as a positive sign. It depends on your choice for studying this free body diagram. But anyway, so if you take upward as a positive sign for y directional force summation, you have vx upward, you have negative p downward, you have negative vx plus delta x, which is also downward, and that's why we put negative sign here, and they must be summed up to be 0. Okay, so what you realize is delta v, which is defined as v at x plus delta x minus vx, must be same as minus p. Okay, so you can see here that you have this external point of force, and because of that we have jump in shear force v. Okay, it's consistent with our example. And regarding the moment, let's take counterclockwise as positive sign and moment summed up to be 0, and we have mx and mx plus delta x, and we have vx multiplied delta x and vx plus delta x multiplied by delta x. And what we realize here is that as delta x goes to 0, we found that this term and this term becomes almost 0 compared to the difference between mx plus delta x and mx. So we realize that the jump in mx plus delta x and mx must be 0. Okay, so regarding the point of force, the relation we can obtain is the jump in point of force v is the same as p, and the jump in I think it must be mistake, it must be minus p here. Jump in moment must be 0. Okay, so you expect in the presence of external point force P, you expect discontinuity in V and continuity in moment M. And but continuity in moment M does not guarantee the continuity in the slope of M. What you can see here is, the slope changes from positive sum number to negative sum number without going through zero. Okay, you suddenly see jump in slope, and why is that? From the previous page, what you can see here is, this is dm dx. This is half vx plus vx plus delta x, and what you can realize here is it's same as vx plus dv dx and delta x. Okay, yeah, if you plug in this relationship, you're gonna realize that dm dx must be equals to be bx plus half dv dx and delta x. What you can realize is when p is non-zero, because p is non-zero, you're gonna have sudden discontinuity in b. Because of this sudden discontinuity in b, you're gonna have infinite slope in dv dx. Okay, because you can possibly have infinite slope, even though your m itself, magnitude of m would not have discontinuity, and dm dx, because of this infinity, can have discontinuity. Okay, so this is the result you can expect regarding this point force case. Okay, so when you see here, when you have point force, you have discontinuity in force. You don't have discontinuity in moment itself, but when you consider dm dx, which is the slope of moment, because that's same as force, you can have discontinuity. Now, as a third external loading, let's consider point moment. As I told you, we're gonna take counterclockwise point external moment as positive sign, and we can set a free body diagram of infinitesimal volume with delta x like this. So regarding summation of a force in y direction, you have vx and vx plus delta x, and you see that the difference and between x plus delta x and vx must be 0, so that even though you have like a point moment, you're gonna expect continuity in v. Now regarding the moment m, what you can expect is, if you sum up m0, this is external loading with respect to c, and you have mx, which is negative sign, mx plus delta x counterclockwise, which is positive sign. You have both clockwise torque, vx multiplied by the half distance is delta x over 2, and you have another I think I made a mistake here. It must be downward. It must be upward. Okay, so you have like a clockwise, which is negative vx plus delta x multiplied by distance delta x over 2, and it must be summed up to be 0. Okay, as delta x goes to 0, what you can expect is that these two terms will be negligible compared to other three terms, and delta m must be same as the difference between moment right after the point moment and the moment just left to the point moment m0, and it must be same as minus m0. Okay, so in the presence of point moment m, you expect a jump in moment delta m. Okay, so to summarize, when you encounter distributed transverse loading, you have v prime x equals to be negative qx, you have m prime x equals to be vx, and if you write down integral equation out of this, this is what you can expect. And regarding the point of force, you have the discontinuity in v, and the jump in v must be same as minus p, and jump in moment m must be 0 when you have point of force only. When you have point moment only, you expect 0 jump, or you expect jump in moment, and the jump magnitude must be corresponding to negative m0. Okay, so with that, we can close the first lecture on analysis and design of beam for bending. Okay, so in the next lecture, we'll try to consider example problem where we can utilize these rules for three different external loading for beam under bending. Okay.